Good afternoon and welcome to our topic. And this topic is presented by me, and I am Haoshi and Tielei Wang. We are all from the Pangu team. Okay, so I guess all the guys come here are interested in the IOS security. In fact, in the past few years, a lot of security researchers already researched the security of the iOS, and a lot of attack surface is already exposed. But in this topic, we will talk about some neglected attack surface in iOS 8, and we will show that based on the previous work, and we put some improved previous work, we could still find some new bugs. And also there are some results in this talk that there are some maybe 0 days and some bugs are fixed. Actually, this topic we prepared is about 2 months ago. At that time, the version is about iOS 8.2. So all the bugs we discovered here, as I promised to on that version of iOS. Okay, so the agenda today, it's just basic knowledge of the iOS security background, and we'll review some old attack services, list some bugs used in the past jailbreak, and then we focus on the kernel part first, see what more we could fuzz in the kernel, and after that we for the userland space, we focus on talking about the XPC service fuzzing, because of due to the time of this presentation, we will focus on some point of the neglected attack service. And finally, there's a conclusion. So as security, I just list some word here. I think we are already familiar with this security mechanism, and the sandbox, the code sign signature, a lot of exploit mitigations, and the data protection to protect your personal information. And maybe in the next major version of iOS, it's iOS 9, maybe the Apple will introduce the hypervisor for the security of kernel, maybe. Okay, so let's go to the first part and review the old attack surface. First, to introduce the userland attack surface. Okay, so we divided the userland attack surface into two big categories, local and remote. And also in local, there's two kind of attacks. The first is through the USB cable. That means you connected your iOS devices to your laptop. And the other is you install the applications, for example, from the App Store or from some enterprise certificate signed application. So for the first type, through the USB cable, that Apple enables you to manage your iPhone through iTunes. So there's a lot of attack based on the iTunes protocol, and Apple supplied some features like the AFC, the file access interface, and you can back up and restore your iPhone, the interface, and also you could just install the application in iTunes. So they have the install D. And another, if you have developed the iOS applications, you could just debug the application on the iOS devices at runtime. This is provided by the Xcode. Also, for the installed application, we give two examples here. And the first is the Jekyll application. This is also released by our team member Tielei Wang in 2013 at the Usenix Security. This application is a special application that uses the private API in the application, but it still passed the review of the Apple and uploaded to the Apple Store. So you can't say that the review of Apple can guarantee that all the applications in App Store is security. And another example here is the mask attacks. This is the published this year by FireEye Research. Actually, this problem is that you could just write an application and set the bundle ID to the exactly same as some other applications, and then you can just replace the original one. That enables you maybe to do like phish or something attack. Yeah, actually the attack through the USB cable is widely used by the past jailbreaks. So, and there's a lot of, for example, in the recent jailbreak, they are able to mount their own fake DDI to on the device, and then can easily get the root privilege on the device. Okay, so for the remote attack surface, actually it's any network connections between in your phone can be an attack surface, and the obvious target is the browser. So for iOS, the browser is the mobile Safari, and this is also where attacked. For example, the jailbreak me by Comics, he used a bug in Safari, and also in mobile Pong2Own, and they can attack your devices and collect your contact information or get your photos. Okay, so another attack surface is message. The first message attack is introduced in 2009 by Charlie Miller, and we are surprised to see that there's actually in this year there also a bug about the message. If you send a special Unicode message to some device, they can just cause the reboot. And the system network demos, this program is actually exists in resolving the configuration profile, network configuration profile. And the demo will crash, and your system is just unresponded. Okay, so this is also released today, this year, sorry. Okay, so after the user learn pass, let's have a look at the kernel attack services. So basically, any communication between the user space and the kernel space could be an attack surface. And there's two ways to trap into the kernel from user space. The first is the BSD system calls, like open, write, read. And the another is a Mac trap. This is very special for on iOS device. So actually, we are able to divide this into some small categories. I just list some here. For example, the I/O control, this API actually is very, very powerful. It's able to control some system variables, read or write some system variables inside kernel. And the file system, of course, if you want to mount an image, the kernel must to resolve the file system, and the device, actually the kernel will provide some functional devices in the /dev/. And another big part is IOKit. Most function is provided by this IOKit interfaces. And another one is the MIG system. We will discuss this later. Okay, so after that, we'll see in the past, a lot of kernel bugs are already used in the past jailbreaks. We'll have a look at them. So to attack the file system, actually in jailbreak me 3, and the kernel bug is that it's a very, very basic stack overflow. There's actually no check of the HFS legacy volume name. So cause the problem is a basic stack overflow. And also there's in Corona for iOS 5, this exploit should be right by the Porter 2G, and he claimed that this is HFS heap overflow. And for system calls, there's some bug in POSIX bar. and in this function, it incorrectly checks the file action data and causes the bug. Actually, this bug is also exploited in the jailbreak for iOS 6.1.3. Okay, let's have a look at the IO control, the powerful API. There's a bug called packet filter kernel exploit. Actually, in this very special handler, inside this handler, it doesn't correctly initialize the member of a data structure, so that causes you could just pass a kernel address inside, and at the end of function, it will decrete the value of the address. That means you are able to decrete the value of any kernel address, so you can change the kernel address data. This bug is used in Limero and Green Poison for iOS 4.1. Okay, so devices. There are also a lot of attack to devices, and there's a very famous bug. It's used in the Evasion 7 for the iOS 7 jailbreak. In this PTMX get IO control handler functions, this handler didn't check the input parameter. When input parameter is the actually the minor number of the PTMX device, and that caused that out of bounds memory access bug. Okay, so the last part is the IOKit. Actually, there's so many bugs in this IOKit, so I just listed some name of them. Actually, in recent jailbreaks, all the kernel bugs exist in the IOKit. Okay, so after we have a look at some past attack services, what will we talk today? Two parts. For the kernel part, we will talk about first how to. There's some small tips to improve your IOKit fuzzing, and beside that, we introduce some more part to fuzzing IOKit, and after that, I will introduce the MIG system, and this might be this is not well fuzzed in the past. And for user space, we will focus on the XPC fuzzings, and we will introduce the work we do. Actually, that is some difference from the work from the Google Project Zero. As we know, they also released some bugs for the userland space. Okay, so let's go to the first part. It's the kernel part. Basically, we see that the IOKit contains more code, so there's more possibility that we may find the vulnerabilities in IOKit part. So we think that the IOKit is really the best target for kernel fuzzing. It's not so hard for you to find some results in this part. And actually, 2 years ago, also there's a topic from Pangu team presented by me and Xiaobo Chen. We talked about how to do the IOKit fuzzing. So we don't give some basic information in this talk. We just give some tips how to improve the fuzzing. Okay, so the first is that we all know that most IOKit fuzzers will focus on calling this function, IOConnect call method. Yeah, this is the powerful functions to do all the tunnels. But if you look inside this function, actually, this is not the lowest function. Actually, this is just a wrapper. This function called IO_connect_ method function, and that function actually is the low-level function. It just called mag message to trap into kernel. So what did the wrapper function do? Actually, they did a very, very simple thing. They checked the size of the input and output structure to determine if the size is very large, larger than the 4 kilobytes, it will tell the kernel you should use an I/O memory descriptor to map this userland memory so you can access it. Otherwise, if the buffer is small, you can just copy in and copy out to access the memory. This is obviously for the performance considerations. Okay, this is a snapshot of the code. You can see obviously here that there's two size check here, and in different branch, and they will pass different parameters to the low-level function. So the idea to improve the previous IOKit fuzzing is that you should not call IO connect method. It is a better choice to call the IO underscore connect underscore method, the more low-level functions, and that gives you the power to bypass the size restrictions. And since some IOKit drivers will for different input, for example, the copy in or for IO memory descriptor, they will go to different branch of code. So by call the low-level function, you can fuzz more parts of the code. And there's an example here. This CV, actually, this is used in the past jailbreak, and this vulnerability code exists in the branch of the driver to deal with a large output structure. But the problem is, if you want to exploit this bug, you should do some heap spray and heap feng shui. That means you need to put the memory into a smaller zone, not larger than 4 kilobytes. Must in a smaller k-alloc zone. So if you call the IO connect call method function, you will not be able to check the bug. So you need to call the low-level function. You can check the bug, and you can bypass the size restriction, so you can exploit the bug. Okay, so another tips is that actually the information leak bugs are really important these days, because if you want to write a working exploit, you need to bypass the mitigations, and the most important mitigations is always the ASLR. So what do we do in our fuzzer? Actually, we check all the possible kernel addresses in all the output of our fuzzing results. So this is useful because we found an information leak bug and used that bug in the past Pangu jailbreak. So besides to improve the fuzz by calling a low-level function, we still introduce some new parts to fuzz for IOKit. This is the shared memory and IOKit traps. So we look at the shared memory first. The shared memory is that actually IOKit drivers is able to share memory directly with the user space applications, and it assumes that the user application already know the structure. I mean, what kind of data you put in this shared memory. So the user space, if wants to open the shared memory, it's quite easy. Just call one API named IO connect map memory after you successfully opening the devices. There's this definition of this function, and this is interesting parameter we should pay attention is the memory type. This flag is meaningful for some IOKit extensions. We see how kernel handle this. So if some IOKit wants to share memory with user space applications, they need to override this function, client memory for type. And this is a simple example code for the HID event service user client. And you can see it's all all the things to do is to return an IO memory descript object. Then the kernel will know which memory should be mapped into the user space. But actually, if you look to some other IO-Kit extensions, as I said before, some functions, some override functions, were dealing with the second parameter is type. This is this memory type passed into the kernel, and you must input the correct type to successfully open the memory. Okay, so the idea to improve the fuzzing, so you try to open the shared memory of an IO-Kit, and you can randomly fill the shared memory while fuzzing the IO connect call method, because some data in this shared memory is used by some internal functions. So you should combine these two together. There are several examples. And the former two of the bugs in IO data queue is reported by Google Project Zero, and the third one is the kernel bug used in the Pangu jailbreak. So we think that the problem in this scenario is that the kernel actually should not trust the memory data may be modified by user applications. You see, the kernel shared its memory to the user space and use the data from the user space. Then you should more restriction and more check on these data, and not easily trust them. Okay, so another part we talk here is the traps. The traps can be triggered by user space by calling the IO connect trap, the 6 functions, and finally they all call the IO-Kit user client trap. The input is quite easy. There's only one index. That's like selector of a function, and besides that, there's there's up to 6 parameters input. Quite a lot. Okay, so how kernel handle this? So if we see the function, we can see that the kernel will first get an instructor called the IO external trap according to the index we input. Okay, and if it successfully gets a structure, and then it will directly call the function point in this structure, and there's no more checks. If some IO-Kit extension wants to provide this feature, they may override 2 functions, but if you look inside, you will see that most drivers choose to override the get target and trap for index functions. So, how to fuzz this part? Actually, first to locate all the overridden functions, and in the functions you could determine the range of the index. So, and then you can do a fuzz because there's no more size check. You just can put 6 parameters. But the problem is that if you find some bug and you analyze it, you will find that the IO external trap, this structure, the definition of this structure actually is different from the word in the XNU source code. There's another member at the end of the structure. We call it flag here at the third word. Actually, if the flag equals 0, that means the second member function is what as we think. It's a real function address point. But if the flag is 1, not 0, that means the function member is the offset of the function in the object v table. So. After I talk about the IO-Kit traps, we move to another part, is the MIG system. The MIG system actually basically is a very, very low-level API called mark message. Or actually, a lot of APIs finally called this one to trap into kernel and dispatch the messages in the kernel. There is a simple example here. Is IO service closed, and you can see that it's directly called make message and send message to kernel. But we have to pay attention here is that there's the message ID. They set a very specific message ID. So how the kernel handle this? All the MAC messages into kernel space were dispatched by IPC kObject server function, and this function find a MIG hash structure in MIG box variable according to the message ID. Okay, and then it will do some check and call the routing of this in this structure. So if you want to know all the functions, you need to locate the MIG buckets. And if you find this in the XML source, where you saw this data actually is initialized in MIG init function, and in MIG init function, it's just read all the data from the MIG-E variable and store them into these MIG buckets. So take a look at MIG-E. Okay, so this defines a lot of subsystems here. So each subsystem will have different function, but you can't find definition in the XML source code. So we go to IDA and reverse the kernel cache of the iOS devices, and you can locate it MIG-E variable and find a lot of subsystems here. And if we take an example here is the Mac VM subsystem, and at the beginning this is the minimal message. And the minimal routine number, actually this is the message ID set in the Mac message function, and also there's a maximum. After that, there's an array of the functions. So after locating all of these variables, you will know what? You will know all the valid message IDs. So when you get these IDs, it's possible for you to roughly fuzzing all the subsystem functions, but the result may be not so good. So in our view, I think maybe more accurately fuzzing must be used to fuzz the MIG system. That means for each functions, for different functions, you need to look inside the functions and figure out what the structure inside this message, so that you can really fuzz these functions. Anyway, I think we think that the MIG subsystems is not well fuzzed in the previous work. So maybe in the future there may be some bugs found in this. But today we just give an example of the result of our fuzzers. This bug exists in the IOKit traps actually. For IOStream user client, override the get target and trap for index function, and there's a you can see in this function actually the A3 is the input parameter. This is index. Okay, so the function restrict the index to restrict the index must less or than 2. But we take a look into the variable he returned. Actually, there's only two elements in this array. That means index 0 and index 1. But if you set the index equals 2, there's an out of bound access memory bug here. Yes, actually, I think this is a very low level mistake for a programmer. Anyway, this code is just unbelievable. Yes, and this bug is still not fixed in the 8.4 version. Okay, so next I will pass to Telly Wang and talk about the userland space.
Hello. Hi, I'm Telly Wang. I'm going to take over the second part. In this part, I will present how we find and exploit vulnerabilities in XPC services. So you may ask, what does XPC means? So In short, XPC is a kind of inter-process communication mechanism on Mac OS. If you look at the applications running on iOS, very likely they are confined by the sandbox. That means these applications have very limited access to the whole system. So to complete a lot of fancy jobs, they have to communicate with a lot of system services so that they can finish the job, do a lot of useful stuff. The design of IPC, inter-process communication, is very good for security because the design makes it possible to separate different functionalities into different processes. And then the system could apply different permissions and also sandbox profiles to different processes. In that case, the system doesn't have to mess up everything together, and that would be very terrible for security. But the potential problem for IPC is that IPC would introduce extra data processing. For example, the client side has to prepare the request and send the request to the server. Server means some system service. And the server side has to pass the request and make a response if necessary. So there's some extra data processing. Apparently, such a kind of data processing forms a new attack, a potential attack surface. And on Mac OS and iOS, actually you can find a number of IPC mechanisms, such as the sockets or distributed objects. And among these, two of the most commonly used with MacMessage and XPC. So for MacMessage, it's the fundamental of all IPCs. It's implemented through the Mac trap called MacMessage override trap. It's the fundamental of all the IPCs. And as a result, if you look at the history, a lot of very good previous work there. For example, the talks I listed in this slide, they discussed the internal details of MacMessage and also introduced how to find vulnerabilities in MacMessage-based service. And compared with MacMessage, XPC is a relatively new IPC mechanism on Mac OS and iOS. It was firstly introduced in Mac OS 10.7 and iOS 5 in 2011. And actually, XPC is built on top of MacMessage. It's just kind of a wrapper of MacMessage, but it significantly simplified the low-level details of IPC. So, in other words, XPC APIs provide a very simple interface to look up the services or connect to the services only by the name. And these APIs are very easy to use to send or receive strongly typed messages. So in a word, it's very easy to use kind of framework to do that IPC. So I'm going to use two pieces of code to demonstrate how to run a XPC server and also XPC client on iOS. So this slide shows the code for server side. And on iOS, the most common way is to use this API, XPC connection, create a Mac service to set up the server. And the first parameter is the name of the service, which has to be reserved in the Mac services of the system plist files. That means basically only the built-in binaries could use API to launch, to set the built-in services. They are not open to third-party applications. And one important parameter is the third one. So basically, the same API can also be used by the client side to connect to the service. The only difference, the only difference is the third parameter. And here, there is a macro. The value, its value is 1. It indicates it's a server. And for a server, that means it's very common to handle multiple connections at the same time. So you may want to have a connection handler. That means you want to dispatch a connection or specify the connection context or whatever. So you can use this API like XPC connection set event handler for the first time, you can set up the connection dispatcher here. And given a connection, you can call the API again, but this time you will set the message handler. And for the message handler, now you are able to get each piece of message. And actually, the XPC message is in the type of XPC dictionary. I will show you later. And but basically, that's how the server side runs. And let's move to the client side. And as I mentioned, the same API is used for client side to connect to the service. And the first parameter is the name of the service you want to connect to. And the only difference is the third one. So now you use 0. That indicates it's a client rather than a server. And now it's time to prepare the message and send it to the server. And basically, you just create a XPC dictionary. It's a key value paired container data structure. You can insert other XPC objects into the dictionary with a key and the value. For example, now in this example, I insert a member. Its name is value1. Its real value is 1.0 in the type of double. And now we can send it to a server and get a reply. So it's pretty easy to use. And this slide summarizes the data flow along the XPC channel. So from the singular point of view, you prepare a XPC dictionary and serialize it into a MAC message, send it to the other process. And from the receiver point of view, okay, you receive the MAC message and deserialize it into an XPC dictionary. And given the dictionary, you extract the XPC objects. And for each XPC object, you can further extract retrieve the raw data, the value, and process the value. So we believe all these three steps, the deserialization, object dereference, data dereference, could be attacked. So here I have to mention the independent work from Ambir Research and Google Project Zero. In this work, he found a lot of vulnerabilities in the object dereference part, a lot of type confusions. And this piece of code demonstrates the root cause of the type confusion. Basically, the server side receives some untrusted message, and the server side also presumes the type of some member objects in the message. For example, in the code you can see, sorry, I only have one level here. So you have the message, and it tries to retrieve the object using the key. And for the returned object, there's no type validation, and the server side continue to just believe it's a XPC type data and dereference the data, because different XPC object has different internal data structures. If you don't perform the type validation, it would cause some security problems. You could refer to Ambir's work for more details about the exploit. And but Apple made a very good response. So what Apple did is it introduced a lot of type checks in all the XPC GET family, that family of APIs. So basically, in the low-level APIs, Apple performs a lot of type validations. If the type mismatch, it will quickly return 0. So it fundamentally fixed all these kind of type confusions. And actually, independently, we find a lot of type confusions on iOS platform, but unfortunately, we find Apple already fixed these kind of vulnerabilities. So we made a step further, and we focus on the data dereference part. So given the raw data, how the server side handles this data, that will introduce security problems. So basically, we want to do some fuzzing, and it's an easy way to test a lot of service. And basically, we have two fuzzing policies. The first one is passive fuzzing. That means we just select a targeted services, and we, by hooking the explicit connection set given the handler function, we are able to get the message handler. We know which piece function will handle all the incoming explicit messages. And we further hook that handlers, and then we can mutate all the received explicit dictionaries and see whether the service would crash, and then we can analyze the crash. And we also want to do some proactive fuzzing. That means we want to proactively construct the explicit message and send it to all the services we can connect. In that case, we may trigger more crashes or find more vulnerabilities. So now the question is, how can we find the services we can connect? You know, I mentioned the sandbox at the beginning, so a lot of services you may not be able to connect. So what we did is, first we decompiled the container sandbox and find all the connectable lookup names. So basically, this snapshot shows a part of the services all the apps you downloaded from App Store. They are able to connect, but some of these services are still using MacMessage. We want to do explicit focused fuzzing. So what we did is we first grab this API, and in that case we are able to narrow the targets, and we can find, okay, these are the services we are able to connect even with the app running in the container through explicit APIs. And the much harder thing is how to construct the message, because you know the server side only retrieve the objects using the keys. The keys is kind of predefined. If you don't know the keys, the server side won't process your message. So the good news is explicit APIs, they provide a set of retrieve APIs for getting the objects by using through the keys. So we just implement a very simple adapro Python script, which will find all the code reference to such APIs, like explicit dictionary get, this family APIs, and we just analyze the second parameter, which are the keys of the objects. So we are able to retrieve all the keys that the server side would like to accept. We put them in the single big, very large dictionary and send it to the server side. So we run the further on iOS 8.2, which was the latest version at that moment. And surprisingly, we found a lot of crash, even the further is very dumb. And some of the crash I will show you might be fixed in iOS 8.4, but we are not sure. And we analyzed these crashes, and in general, we classify them into 3 categories, and we will go through each one by one. The most typical case is null-pointer dereference. So the root cause is the server side just presumes the existence of the certain keys in the message. So it just tries to retrieve the object, but doesn't check whether the pointer is 0 or not, and continue to use that pointer. Definitely that will trigger the crash. And in this page, you will see this is a piece of decompiled code, and this is the path of the executable. And below, you can see the POC code to trigger the crash. And now, pointer dereference is not a big deal, but for the IPC scenario, it's a little different. So because if this application is kind of malicious, it can crash some services. That means even all other benign applications are not able to use any services. For example, if I can crash some very important service in your iPhone, let me trigger some kind of denial service. And let's move to the out-of-bound memory read. There's a program called, I just show you some typical example. Actually, we find a lot of similar problems. And this is the CVM server program is a component of OpenGL EX. And in in this page, you can see at the beginning, the server side tries to retrieve the object using the key X, which will return, is supposed to return a binary array, just a raw array. But the program doesn't perform any length check and directly pass the buffer to another function. Inside of this function, you can see it tries to dereference the value with offset 8 and 12. So for example, you just pass the array with length of like 4. Definitely, if you want to access the offset like 8 or 12, it will trigger the out of bounds read. And then you can also find the POC code here. And besides the memory read errors, we also find a lot of memory errors in this library. You can find the source code of this library and and Apple's website. And let's quickly go through the source code. You can easily understand why they made the mistake. So basically, this API is used to get the DNS configuration through XPC services. And basically, the data ref is retrieved from the XPC message, and there's some data propagation, but it doesn't matter. Finally, the data is passed to the function named expand configure. But the code totally trusts the value inside the message. And for example, it directly uses __ attributes as the array index. If you are able to control the message, you can set up a super large value here. Definitely using this as the index, it will trigger the memory error. And finally, I want to share a remote code execution bug in a program called IAP Transport D program. And it's a very kind of surprising bug to us. And let's go through the code quickly again. And basically, the server side tries to retrieve the object using the key port ID. And this API will return an integer. And but the server side simply uses the integer as the object pointer. Here you can see it tries to make a virtual function call, but the object pointer is passed from the client side. So basically, you just construct the value and send it to the server side. It will trigger some memory crash. But for this bug, it's very easy to exploit. Why? So the key point is how to control this expression. So the short answer is to use the pip string. You can refer to MBL's work to say how easily you can send a very super large XPC message and affect the heap layout. So basically, it's very easy. And for the second problem is because of the code signing mechanism and the DEP mechanism, you are not able to jump into the injected shellcode. You have to leverage existing code. That means you have to use ROP-like technique to implement the shellcode. And the good news is, on iOS, all the dynamic libraries are merged into a same catch file, which is shared among all the processes. So if you find a gadget in your own process space, that means you can find the exactly same address in other processes. So RP is just super easy. And let's talk about the impact of the bug. Okay, so first, this service is connectable by any applications running in the container sandbox. So that means any application you downloaded from the App Store is able to exploit the vulnerability. And the second consequence is, for the apps you downloaded from App Store, it's confined to the sandbox. It cannot touch a lot of system files or private information. But the app, if it's malicious, it can exploit the vulnerability in the program, in the system service, and then it can easily bypass the sandbox and gain more access to your system. So we believe it's a pretty dangerous bug. And so let me conclude the talk quickly. We reviewed the attack surface in iOS 8, and we demonstrated how to improve the fuzzing to find vulnerabilities. So generally, LKIT fuzzing is not new. IPC fuzzing is not new. But if you combine these previous techniques with new improvements, with some new tricks, it's not surprised to find new vulnerabilities and more findings. And also, we believe that Apple puts more efforts on improving the whole security architecture rather than fixing individual bugs, like what XPC did. But if you make a step further, maybe you can still find bug vulnerabilities. And because the XNU code has a very long history, we believe that reviewing all the very old source code is very helpful to security. Okay, thank you for your attention. We are glad to answer your questions.